All right. So for those of you who are not familiar with us, we are a small software startup company located in Connecticut. We specialize in mass spectral calibration and mass spectral identification and analysis. We have a commercial product which you will be able to learn a couple of features throughout this presentation. In terms of unknown formula identification or elemental composition determination, to be more accurate, the Journal of Organic Chemistry guideline is perhaps a pioneer in the field in terms of specifying what may be required for organic compound confirmation or unknown identification. The first generation of the guideline calls for a high-resolution mass spectrometry to be used to identify or confirm any organic compounds to within 5 parts per million mass accuracy, and that has sort of become a industry standard. Unfortunately, for the older mass spectrometers, such as the magnetic sector instruments, achieving 5 ppm mass accuracy is a relative mass error. For a smaller molecule like 100 Dalton would have been very, very difficult and utterly unnecessary, because it's a smaller molecule. You don't have nearly as many choices or ambiguities. So after intense lobbying from the ISMS work group, the guideline has been revised later to specify that a mass spectrometer of high enough resolving power so that you can be reasonably sure for the lack of interference, which is much more reasonable requirements. And also the 5 parts per million mass accuracy has been changed to 3 millidalton mass accuracy, from a relative mass error to absolute mass error, which is a lot more reasonable. This guideline is a good step forward, but it's not quite right yet either, as you will see from this next slide, where for a smaller compound at 91 Dalton, for example, if you can measure the mass to within plus minus 3 millidalton, there is only one possibility. So you would have either confirmed the organic compound, the synthesis, for example, or you would have identified the compound uniquely with very high confidence. The same 3 millidalton plus minus mass error, when applied to a 400 Dalton compound, the choices suddenly becomes so many. You suddenly would have 317 possibilities, which makes it nearly impossible to identify true unknowns. And for organic synthesis confirmation, you would have the right compound within this one out of the 317 candidates, so you would still be able to confirm the organic synthesis. Unfortunately, you will be confirming it at a much lower confidence, because it's 1 out of the 317. And because of that, the industry has moved to develop higher and higher resolution systems with higher and higher mass accuracy, by focusing somewhat exclusively on determining the mass accurately for the monoisotope peak of a compound. And there has been a tremendous progress made to make that single point measurement more and more accurate. In the process, some of the other important information in the spectral domain has been pretty much ignored, unfortunately. For example, for this particular compound that contain 25 carbon, 23 hydrogen, and so on and so forth, you can calculate the theoretical isotope distribution, which would be a discrete distribution. And if you blow up the A+1, you can see that it's not just a single centroid or stick. It contains additional isobars that are very informative in terms of elemental composition determination. It will tell you whether you contain carbon, hydrogen, nitrogen, and oxygen, and sulfur, and so on and so forth. So they're very indicative and extremely important as far as elemental composition determination is concerned. Now, if you go to a higher isotope, such as A+2, the intensity is weaker, but you certainly have even richer information because there are many different ways to combine various isotopes of the atoms to form A+2 isotope cluster. And they are extremely important in determining whether you have a compound that contains sulfur, for example, or some other elements, and how many of them you might have. And those are the spectral information that get lost in the conventional processing through, for example, centroiding. We have done some work using a very conventional mass spectrometer, such as the unit mass resolution system, and to analyze and see if indeed we could tell very similar formulas apart from each other using a lower resolution system by looking at the mass spectral domain information. And in this particular case, we have 5 possible formula candidates, and their monoisotope mass is within 100 ppb of each other, very, very close in terms of mass error. But spectrally speaking, as you can see by the through the spectral overlay, spectrally speaking, they're very different. On the A+1, we have mass spectral response that faithfully represents the contribution from carbon-13, sulfur-33, nitrogen-15, and hydrogen-2, and so on and so forth, so that if it's a different elemental composition, it will have a different profile. If we can analyze and process the mass spectral data in the raw scan profile mode. The processing of raw scan profile mode requires, however, a different type of mass spectral calibration, which you can see on this next slide. Because the conventional mass spectral calibration would require a standard of known elemental composition, and it will just set up the mass spec to run in the profile mode, either during the mass spec tune process or during a more elaborate and separate instrument calibration process. And then once that standard has been measured, the peak apex of the monoisotope position would be calculated, and then it will be compared to the peak apex of the theoretical calculation. And in this case, there's obvious difference between the peak apex. And then the conventional mass spectral calibration, regardless of which vendor you might use, would perform a mass spec calibration, which does nothing more than simply moving or shifting the actual measurements to line up with the theoretical measurements so that the peak apex is calibrated, so to speak, leaving another spectral error in the rest of the mass spectral data. And that sort of spectral error on the order of 5 to 10% overall is perhaps all the difference there would be between one elemental composition and another. So it would have destroyed the differentiating power to tell one elemental composition from another. So that's the type of mass spec calibration that will have to be improved upon in order to take advantage of the full spectral information that's available from mass spectral measurements. So we came up with a different type of mass spec calibration, where during the calibration process, we transform the actual measurements into the red trace, where not only the mass is calibrated, but the whole spectral profile, including the peak shape, is also calibrated. And in the process, we achieve something that's quite remarkable, where we have not only mass accuracy, but we also have spectral accuracy. The whole spectral profile would be overlaid almost exactly with the theoretical calculation, subject only to random noise, of course. And the details of this algorithm and the rationale behind it has been pretty well published in this front cover analytical chemistry article, which is freely available as a download. I will provide a link where you could download this article, which goes through some of the details of the calibration process and the mathematics that goes with the calibration process. So we implemented this this calibration and technology and the corresponding analysis technology to perform unknown identification using even GCMS system with a single quadrupole, for example. And with a spectral accuracy now, you can eliminate the incorrect formulas by simply clicking each formula candidate and see how the spectral match works out between the calibrated trace and the theoretically expected trace to determine what's the right elemental compositions. This is so easy to use and so interactive that it can be used as a very interesting and extremely valuable teaching tool to teach undergraduate and graduate students about accurate mass, unknown identification, isotope distribution using the conventional benchtop system that they might already have in the instrument lab. So there's a lot of interest from the education community, chemistry department, instrumental analysis teachers to be able to use the software to teach the next generation of mass spectrometrists how the unknown identification works with accurate mass, with isotope information, and to be able to see interactively how the spectral response match what you expect in theory. So in the latest version of the software, we have also built in a list library search for GCMS application. So you can simply right-click, and it will send the spectrum over to the list library with accurate mass information to go with it, so that when you compare the spectral match, you can now have accurate mass available to compare with the exact mass information that's available in the latest list library 14. Other new features are forthcoming, including sending the formula that you have identified as a possible consideration into a web, into ChemSpider, for example, to see how reasonable this elemental composition may be by looking at the structural information and other information that's available from the web. So while this is terribly useful, but the hardware manufacturers have continuously been improving the hardware to higher and higher resolution systems. So, for example, you would now walk into a mass spec lab and to see a typical LC TOF or even GC TOF system that's a much higher resolving power. And the question is, what can we do there in terms of spectral information to help us even further on the time of flight medium resolution system, so to speak. As you can see here in this particular example, we have unknown at 844.5, and it's a time of flight system. So the resolving power is such that there is a well baseline separation between A and A+1, and so on and so forth. And that makes it very interesting in terms of what we can do to further improve the elemental composition. But at first, we would go ahead and perform unknown identification using conventional accurate mass determination and accurate mass elemental composition search. So we would punch in the typical suspects, in this particular case, carbon, hydrogen, nitrogen, oxygen. Notice we're not opening up to all possible organic compounds, such as organic elements that could make organic compounds such as fluorine, phosphor, and so on and so forth here yet. Because of the large mass involved, it would have been overwhelming in terms of possible candidates. So we stick to the basic elements CHNOS, and because it's accurate mass measurements, so we would search within plus minus 4 ppm mass accuracy and see what we would get. So this is a pure conventional search. It turned out at such mass we would get a total of 90 possible candidates within plus minus 4 ppm mass accuracy. And here on this slide, we listed the top 20 candidates that comes within 1 parts per million mass accuracy. So had we been terribly aggressive in setting the accurate mass window tolerance for the search, this would be the only 20 candidates we have to contend with. And the right elemental composition better be within the top 20, or else we're going to miss it completely. In this particular case, we have the number 21, which happened to be slightly outside of the 1 ppm mass tolerance window. So that's why it ended up as a number 21 candidates. So in our software, you can click this particular candidate, number 21, and it will do a spectral overlay to show you what the spectral match is between the raw mass spectral measurements, the red trace, and the blue trace, the theoretically calculated mass spec, should this be the right formula. And right away, you see a significant mass spectral difference across the whole range, and that can be confusing sometimes. It could be because we have the wrong formula, therefore the theoretical mass spec doesn't match the actual measurements. It could also be that this particular mass spectrometer has a particular peak shape due to the ion optics and other factors that impact the mass spectral peak shapes, such as detector systems, the reflectrons, and the acceleration fields, and so on and so forth. So it could also be a combination of those two. So it's a little difficult to tell what may be going on here and how we would evaluate these particular formula candidates. Fortunately, you don't have to deal with the uncertainty that comes with the mass spectral peak shape, if only we have a way to calibrate the peak shape function, therefore removing it from consideration and leaving us only with apple-to-apple comparison. When we compare one formula to another, we are only dealing with elemental composition differences. We're not dealing with peak shape differences from this particular mass spectrometer. And this is done without even any standards. In a process we call SCLIPS. It stands for Self-Calibration Nine-Shape Isotope Profile Search. So here's how it works. We use the monoisotope peak of the unknown itself to perform a peak shape only calibration. We do not perform mass calibration anymore. That's why we don't need our standards. And we rely on the fact that the monoisotope peak of the unknown is pretty well measured, and it's a very good representation of what the mass spectral peak shape function is at such mass and at such time. And then we would go through a calibration process, which is not very different from the conventional calibration that we perform for single quad or triple quad lower resolution systems, to come up with a calibration function that's similar to what we have before for lower resolution systems, so that this calibration function, when applied to the rest of the isotope cluster, would convert and transform the raw measurements, the black trace, into the blue trace, where the blue trace would have a perfectly defined mathematical peak shape function. And that perfectly defined mathematical peak shape function would then be used to calculate the theoretical mass spec for any particular formula candidates, so that if we have the right formula candidates, they better be right on top of each other. subject only to hopefully random measurement noise, so that we can perform a full spectral match in the raw profile mode without regard to the particular instruments that did the measurement, which brings its own particular peak shape function. We have removed the peak shape function from the consideration completely, and which would allow us to measure and compare different elemental compositions. So after the peak shape calibration, here's what the spectral match would look like. We have the green trace, which is a theoretical mass spec, matched to the calibrated trace, the blue trace, and you can see that it's almost perfect. The spectral accuracy is 99%, and you can, in the software, you can click the spectral accuracy here on the header. It will sort the 90 possible elemental compositions based on spectral accuracy instead of mass accuracy. And this number 21 hit from this mass accuracy hit would now be the first hit in terms of spectral accuracy. You might ask at this point, well, we happen to be lucky, perhaps we got the first hit as a correct high spectral accuracy hit formula. What does number 2 look like? Would it be very different? Well, indeed, number 2 actually is very similar. It has 98.6% spectral accuracy. So you might have to consider number 2 as a possible candidate as well. But number 3, however, has only 97.3% spectral accuracy. And as you can see from the spectral overlay here, there's a significant error on the A+1. And you know that this would not have been the right elemental compositions. So by going through the F-CLIPS calibration process for a medium resolution system, such as a time-of-flight system, we can significantly enhance elemental composition determination by reducing the number of possible candidates from 90 to maybe 1 or 2, sometimes at most 3, for consideration. That's a tremendous improvement in what you have to contend with. The same approach has been applied to an older first-generation Orbitrap system. It was published by our customer at the Novartis, at the YS, I'm sorry, where he evaluated comprehensively the spectral accuracy and its impact on elemental composition determination using LTQ Orbitrap system. What he concluded is that through the use of F-CLIPS calibration to remove the peak shapes into consideration, he could eliminate up to 99% of incorrect elemental compositions and deal with only the top 1% of the possible formulas when doing unknown identification. And this is a paper that's published in the Journal of ASMS in year 2009. It's a very interesting paper. It studied the impact of different masses and different resolving power on the spectral accuracy. And that was done. Those days, however, we have even better and better instrumentation now. It is now possible, for example, to reach 100 parts per billion mass accuracy with higher and higher resolution systems. You can reach a resolving power of more than 1/4 million to 1 using Orbitrap, using some of the newer Orbitraps, or the conventional FTICR mass spec systems. As long as you are careful with concentration, space charge, and you recalibrate and so on and so forth, it is within reach now in terms of the state-of-the-art mass accuracy to be able to measure mass error down to be able to control mass error, rather, down to less than 100 ppb. For a true unknown, however, you have to consider other elements more than just this carbon, hydrogen, nitrogen, oxygen, sulfur. So in this particular case, we open it up, we consider CHNO, fluorine, sodium, sulfur, and phosphor. Even with such high mass accuracy, we would not be getting a unique formula. We get pretty close. We get 7 possible candidates. And out of the 7 possible candidates, by using smart chemistry, you can perhaps eliminate a couple. In this particular case, you might be able to eliminate the elemental composition that contain 2 sodiums or 3 sodiums, based on the fact that it's rare to see a singly charged ion with more than 1 sodium involved. As you know, however, this is not unheard of, however. For example, the sodium TFA would contain multiple sodiums, yet it would be singly charged. But by taking that a little bit of a risk and using chemistry knowledge, you might be able to narrow it down to the top 5 candidates to look at and to investigate. But at this point, with such high resolving power, you might wonder what utility there may be in the higher isotopes, and what would the higher isotopes look like? Well, we did a computer simulation to see what those 5 formulas are going to look like on a perfect computer simulated FTICR system. So on this scale, you don't see much of a difference. So I'm going to blow up the A+1 to let you see what the fine isotopes would look like at 800,000 to 1 resolving power. At such high resolving power, even the fine isotopes are baseline resolved, which lend itself to a nice spectral interpretation. You could actually put your finger on the individual fine isotopes and to figure out which one is which. Well, for example, the first pick is here is nitrogen 15, and the second one is sulfur 33, and the next one is carbon 13, and so on and so forth. Now, had the FTICR or ultra high resolution system been perfect, or even close to be perfect, the elemental composition problem would have been solved, because you don't need to do any elaborate calculation. You could just go in here at the A+1 cluster and count the relative abundance of the nitrogen 15 peak, for example, to decide how many nitrogen 15s may be involved, and likewise to determine how many sulfurs may be involved and how many carbon may be involved, and so on and so forth. I don't know if you have wondered, the literature has very little publication on this subject. And you might be wondering why people are not doing ultra high resolution fine isotope counting to determine elemental composition. Well, there may be some carbon counting papers out there. There may be a couple of sulfur counting papers out there. But by and large, elemental composition determination has not been performed by fine isotope counting. And we have wondered about the same question. And did a little bit of an investigation with our customers and collaborators. And I would like to share some of the interesting findings with you in the next couple slides here. So here is a data set that was acquired using Orbitrap Elite, which is capable of operating at 240K resolving power. We turned the AGC on by default, and we wanted to see how reliable the fine isotopes would be on the A+2 isotope as we move across the chromatographic peak on the top, as shown here. As we move across the chromatographic peak, how does the A+2 isotope measurement look like, and whether they are good enough for a fine isotope counting for the purpose of elemental composition determination. So we take the peak apex first here, and we get the A+2 isotope fine structure measured there. Looks very high signal noise, and that looks just fine. It's comforting that we see baseline resolution as we expected. And then we move down the slope, take out another scan, and suddenly the two peaks here, the intensity seems to have been reversed. And that's a little bit of a mystery, why that would have happened. We seem to have very good signal noise. And then we move on to another point on the declining edge of the chromatographic peak, and we get another scan here. And on this scan, even more mysteriously, the other peak just totally disappeared. We have only two peaks observable for A+2. And then we move down close to the baseline, but still above the baseline, and we now see two peaks in this region, and with relatively comparable isotope abundances. And this is mystifying and extremely puzzling in terms of unknown ID, because which scan should we trust, and which one would be the one that we would base off to do the fine isotope counting to determine whether we have particular elements or not, and how many of these particular elements there may be. So we were in a little bit of a bind as to how to proceed. Well, if only we know what it was that we are dealing with, then it would have been easy. If, for example, in this case, we actually knew what it was we're looking at. We had the elemental composition information to start with, so we could actually perform a theoretical isotope distribution calculation and do a spectral overlay and see where we would be expecting various fine isotopes. And we can even label some of the corresponding key peaks as to where they may be coming from, which elements and how many elements there may be in order to have such intensities. So we can see here right away this scan at the peak apex has significant error. It would not have been able to help us count out the particular element. So we move down and take another look at the peak, look at the scan, and with a spectral overlay, it looks like this one is not going to give us what we need either. And we go down to the third scan here. Again, it would not help in terms of unknown identification or isotope counting. This scan right above the noise on the declining edge seemed to be the best match between the actual measured and the theoretical they expected. So this would have been a sweet spot, unfortunately only in hindsight. That is, if we know what we're looking for. But what will happen if we actually have to deal with a true unknown, that we don't know what the elements it might involve, and it's a real unknown impurity. But we do have so much data, ultra-high resolution mass spec available. Can we do something about it? That was the question then. Well, since this is a true unknown, so we're going to call that unknown, and we're going to involve all typical suspects that you might expect in an organic compound: carbon, hydrogen, nitrogen, oxygen, sulfur, fluorine, phosphor, iron dye even. And it's relatively high resolving power and high mass accuracy, so we're going to search within plus or minus 4 ppm to do a true unknown identification. But the question is, which scan should we use across the chromatographic peak to do the analysis, and how do we know? How do we know beforehand, not after the fact? So the mathematical setup is a global search. The question is there enough degrees of freedom in the data that will allow us to search for an extra unknown parameter? This extra unknown parameter is the best mass spec scan number, while searching a true unknown elemental composition. So instead of determining how many carbon, hydrogen, nitrogen, oxygen, sulfur, phosphor, fluorine, iodine that might be involved. We also would like to determine this extra parameter, which scan to use. And is that possible? And in the process, we need to use a matrix. How do we know which scan to use, which scan is good? How do we evaluate each scan, and how do we evaluate each elemental compositions? Well, we know we can evaluate each elemental compositions using spectral accuracy from the medium resolution system, such as time of flight, or from a particle system, low-res system. It has worked out very well, served us tremendously well. So maybe we can use the same spectral accuracy matrix to evaluate not only elemental compositions, but also to evaluate each and every single mass spectral scan to come up with a global solution to the problem. Will this be possible? Well, we went ahead, being a startup, we went ahead and implemented in the latest version of the software soon to be released, what we call the best scan S-clip search, where the user would mock up a RT window to look at, to compare various different scans, and to set up the global true unknown identification, considering all typical suspects, perhaps all suspects for organic compounds, and let the computer go and do a global search to tell us which scan to use and what the spectral accuracy would be when we use each and different scans. And here is the intermediate results, where for each scan, we perform a true unknown search across the chromatographic peak, and we plot the top elemental composition and its corresponding spectral accuracy across the chromatographic peak. As you can see, at the peak apex, that's where we have the largest spectral error. We only get 90% spectral accuracy, with about 10% spectral error. And on both ends of the chromatographic peak, we seem to be getting decent spectral accuracy on the order of 97%. And the best scan was found to be this particular scan, where we get more than 90% spectral accuracy. So let's go in and take a look at the list of formula candidates sorted based on spectral accuracy. Well, it turned out we have a total of 36 possible candidates, and out of which the correct elemental composition does come up on top of the list with the highest spectral accuracy of 97.7%. So the idea seems to have worked, and the elemental composition can be treated as unknown, and the best scan can also be treated as unknown in this exhaustive search, which can be performed relatively quickly to be practically useful. Of course, more testing needs to be done, so the work will be ongoing with our collaborators to do further investigation and application and analysis. So just to summarize it up for you, the mass accuracy, of course, is extremely important from either single quad or triple quad lower resolution systems to time of flight systems or to the ultra high resolution systems. It's a very useful measurement. And we have found over the course of our studies, and many of them, that the spectral accuracy in many applications, particularly for elemental composition determination, is even perhaps more important to help identify the right compound. And the peak shape calibration is really as a key, whether you have a low resolution single core systems or higher or ultra high resolution Orbitrap or FTICR system. It enables elemental composition on an otherwise a conventional single core system, but it would also help higher resolution systems significantly. On the higher resolution systems, for the medium resolution systems such as TOF or older version of the Orbitrap, we can help eliminate up to 99% of the incorrect formulas by the use of spectral accuracy and by the use of a special procedure to calibrate the peak shape that we call S-clips. For the ultra-high resolution systems, it seems that we can perform a scan-by-scan spectral accuracy analysis to help achieve true unknown identification, where you have no idea whatsoever what the impurity, what the contaminant, what the unknown may be. When you are running at the ultra-high resolving power, where the fine isotopes can be measured and can be resolved. We have other applications that takes advantage of the spectral accuracy concept and the calibration process, which I don't have the time to go through today, but I just want to mention them. For mixture identification and mixture quantitation, for example, hydrogen deuterium exchange experiments, the carbon-13 stable isotope measurements, these are using metabolic flux analysis or drug metabolism or plant metabolomics applications. For the large molecules, biologics deamination, that's another wonderful application where we have demonstrated by calibrating the mass spectrometer, typically the high resolution systems in this case, to high spectral accuracy, we are able to determine down to 1% deamination impurity, even when they are not separated from the native compound, for biologics applications based on either protein or peptides or oligo drugs. So with that, I would leave you with this final slide where you can get further information, including a free download for the analytical chemistry from cover article, some videos, technology demos, and some training demo videos. And you can also look up detailed applications, papers, and ASMS posters under our resource directory on our website. Feel free to contact us at info@cernobioscience.com if you'd like to learn more about the software. We encourage you to submit some data, run some data, and work with us through WebEx to show you how it all works on your data, on your mass spec systems, working with your sample. Most importantly, I'd like to show our gratitude to the many brave early adopters and out-of-box scientists and researchers who are willing to listen to us and work with us. In particular, many collaborators, especially Dr. Christine Gu from Genentech and Dr. Bob Strife from P&G, who have been working with us on this ultra-high resolution application, with both of them, our collaboration continues, and we'd like to thank them all. And thank you all for the opportunity to share with you some of the work we have been doing. And we would be very delighted to work with you and to interact with you as well. So with that, we'll conclude the recording of this webinar. And I would be more than happy to answer any questions that would be coming through the chat box. Thank you all.